Quand il commence à parler du truc là de l'arbre, il faut reprendre la base de la famille, c'est la base noire.
So, good morning, everyone. So let's begin.
J'ai essayé, mais je n'ai pas réussi. C'était la troisième, c'est pas
Okay, so please get seated. Let's begin. All right, so we're working on the worksheet, the addendum 233, which is just we're going to consider many different kinds of linear maps. Oh, well, many different kinds of maps. First idea is we have to show that they are linear indeed, and then find out that kernel and image, and whether we have an injective map, surjective, maybe an isomorphism, and all that things, right? Okay, so the first two ones, so I asked you to prepare that. So I assume you have tried at least a few of those, okay? So, first one, so that's worksheet 3, addendum. Okay, so the first map is a map from R3 to R3. We've got so for any x in R3 gives you A times x, where A is the 3-3 matrix 1, 0, 0, 1, 1, 1, and 1, 2, negative 1. So what about, is that linear? Yeah, okay, why? It's a matrix, right? That's enough to say that it's linear. If you need to show that indeed it satisfies the usual property of linearity, but just saying it's a matrix is enough. But if you really want to show the linearity property, you take x and y in R3, you take lambda in R, and you take A applied to, well, linear map A indicated with a small letter applied to the linear combination, lambda x plus 1, is given by the matrix multiplication, or matrix is the capital A matrix, this one, times the vector of R3, that is the linear combination. And of course, the linearity property is satisfied because this is the linearity property of the matrix vector multiplication. Okay? So, yeah, and so then we have that this is lambda A of x plus A of y, so indeed we have linearity. Okay, so I've done the proof here. The proof is this one. The image of a linear combination is the linear combination of the image. Okay? But basically, if you have a matrix, you know it's linear. If you have matrix multiplication that define your linear map, you know it's linear. Yep.
Just what you said. So every time you have a matrix, you know it's linear.
Yeah. If the map is take a vector and multiply it by the matrix. Yeah. If your linear map is defined by a matrix, then it's linear. And that's the beauty of what we have proved. It's that if you have a map, a linear map from a finite dimensional space to another finite dimensional space, you can represent it with a matrix. Okay, that's the main result of last lesson. Right, so you can represent it with a matrix, and well, linearity is just directed. Okay? So, kernel image of this one. Do you want to come and do it, please? Yes, very good. Yeah. Okay. So the kernel of this linear map, can you stop for the image? It's just the null space of the matrix. Okay. Kernel is just a more general way that we can use for linear maps in general, whereas null space is really related to matrices. Okay. In French, we just use kernel. The same word, kernel.
For the image, I did something different. I took this as E1, E2, E3.
Yeah.
And then I just did A of E1, A of E2, A of E3.
Yeah.
And this gave me the...
That's an interesting way to do it. Yeah, sure. Well. All right. No. Why did you choose these as the vectors?
I don't know, because I did like the image of A should be of dimension 3.
Yeah.
Because kernel is dimension 0.
Yes.
And it should be equal to the dimension of R3, which is 6.
Yes.
So, yeah.
Okay. I think you're mixing two things, right? First, I will do it. The first thing is that what did you learn during semester 3? What's the image of a matrix or a linear map? If it's represented by a matrix, it's just the column space, right? Image and column spaces for matrices are exactly the same. So you know how to find this, okay? What we learned during semester 3, so you can work directly on the matrix. You make it as a row echelon matrix, and the spanning family for the column space is going to be the columns that correspond to pivots. Okay, that's what we learned from semester 3. Okay, we did this CR decomposition, and then it became obvious, right, that the pivots, the column corresponding to pivots, were the one you would use to reconstruct your whole matrix. Okay, right? So this is something you can do. Another thing you can do is, but then it's going to be obvious. Right. The other thing you can do is remember that the image of a map is spanned by the image of a basis. Okay, I thought that this was the reasoning you were doing. Okay, so when you want to do this kind of thing, what is the easiest basis we get? The standard basis of R3. Okay, what is going to be so we could check for the image of E1, E2, E3. Okay, so with the standard basis, E1 being just the 1, 0, 0, E2 being the 0, 1, 0, E3 the 0, 0, 1. Okay, and then you look for the dimension of what is spanned by those three vectors. Okay, but let's see what we get. What is the image of 1, 0, 0, 0? 1, 0, 0. What do we get? Okay, so 1 times this plus 1, and then 1 times that for the second one, and 1 times this for the third one. So what do we get? The first column. To get that element, first row times this column, that gives me the 1. Second element, second row times this column, that gives me also 1. Third element, that row times this one, that's giving me 1. What do we observe? That's exactly the first column of the matrix. Guess what? If you're doing A times E2, what are you going to get? The second column. Okay, that's exactly the second column, 0, 1, 2, and A, E3 is going to be 0, 1, -1. If you want to be convinced of that, just do the calculation. Okay, but this is what we get. We had this section of the chapter during semester 3, where you have those 36 views of matrix multiplication. This is really what it is. Okay? When you are multiplying a matrix by a vector, each component corresponds to what's happening with the corresponds to what's happening for the first column. The second component is corresponding to linear combination of what's happening for the second column, and so on. Okay, that was one way to see that. Okay, but let's just go again on that. When you're doing this matrix, let's say it has column 1, column 2, column 3, times x, y, z. Okay? What you know is that this result, you can write it as x times column 1 plus y times column 2 plus z times column 3. That's something that we have seen. Okay? All right, so what do we find again here? We find that this x, y, z vector, that's actually something that I can write as x times e1 plus y times e2 plus z times e3. Okay? So when I want to apply my matrix A here, what do I get? I get that this is going to be, I'm going to use linearity. X, y, and z are just numbers. E1, E2, E3 are my vectors. I will get x times A E1 plus y times A E2 plus z times A E3. Okay, maybe I can put some arrow just to distinguish that capital letters in the matrix. This is just numbers, so I can put them in front of my map, in front of my matrix, and these are really not vectors. Okay? So what do we get? The image of anything is written as linear combinations of the images of the basis vectors. Okay, so we're all turning around the same idea. Okay, it's always the same thing that we're writing. So that's why when you want to get the image, you have, when you don't really know how to do, one idea is just take the image of the basis vectors, of the basis items, and see what it creates. Right? What's happening is that those three vectors are going to be linearly independent. Okay, so this you can check by doing the, for instance, the determinant, which is very quick to get. Right? If you do the determinant, you get 1 times this one, which is not 0. Okay, so you get that they are linearly independent, so that they have the this linear combination are going to be dimension 3. Okay, so well, we have everything that's. We always get back to the idea. I knew that it would be dimension 3 because the kernel was 0, was reduced to the 0 element. So you, according to the rank nullity theorem, we also get that if the kernel only contains 0 element, it has dimension 0. So the rank has dimension 3, rank being the dimension of the image, so it's R3. Okay? So you have many ways to get there. I would say the simplest would be, so we have this matrix, so it's linear because it's a matrix. Either you look for the rank by doing the reduced echelon form, and well, which could also help you get the kernel. By the way, they're really complement ideas of each other, right? So if you get if you're looking for the null space for the kernel and get that it's 0, okay? So from rank nullity theorem, we get that dimension of the image is going to be, well, 3 because that's the dimension of the domain, minus the dimension of the nullity, which was 0. Okay? Okay, so I know that dimension of the image is 3. The image is in R3, so image of A is R3. Okay, because it's the only linear space of dimension 3 that belongs to R3, that is included in R3, is R3 itself. Okay? Right, so you have many ways to get to this result. One, maybe the most direct was to solve for the kernel, get that the image is R3, and that's it. Okay, so is that an isomorphism? Yes. Okay. Why? Because first it's injective, because the kernel contains only 0, and then it's subjective, because the image is the whole space. Okay, the whole codomain. Right, so it's indeed an isomorphism. Yep.
If the kernel space is equal to 0, so it's injective?
Yes. Know how to prove this. Okay, the proof is in the lecture note, the proof is in the videos, I guess. It's not a complicated one. Yeah.
Is the image the span of every columns of A?
Yes. Why? Because of this. Okay, the image is everything you get. Everything you get can be written by this relation. Okay? Okay, so, and that's also in general, the image is defined by all the linear combinations of images of a basis. Okay, so all the linear combinations I can make with A of E1, A of E2, A of E3, that's how it's written. Okay, so yeah, that's the span of these, and these are the columns of my matrix. Okay, and you get back to the first definition we had, of the image of the column space. It has the name column space because it's all the things you can create with taking linear combinations of the columns. Yes?
Can you repeat why it's subjective?
Because the image is the whole codomain.
Okay.
Okay? So, onto is subjective. Okay? Injective is one-to-one. And bijective or isomorphism is one-to-one, and onto. Okay, so subjective is really you span the whole codomain. Right, so the idea of all these exercises of today, of this worksheet, is really to see what are the more illustrative possibilities for these ideas. Okay? Right, so that's one. You were supposed to be able to do this completely at the end of last semester. Okay? Looking for null space and column space. This is, and checking the rank nullity theorem. These are things we did last semester. Okay? Just now we have enriched our comprehension of this, right? With the whole framework of the linear spaces. It's more general. Okay? All right, so the second one is now a non-square matrix. So if it's not a square matrix, I'm sure of one thing. What could it be? From the rank nullity theorem, okay, if I have a non-square matrix, I have one certainty. Yeah?
It's not an endomorphism. No.
Oh, yes, yeah. That's true. Endomorphism because it doesn't go from one space to itself. They have different dimensions. That's true, yeah.
It's not subjective.
It's not?
Subjective.
It depends.
Objective. It's not objective. It's not objective.
It depends also. One of these will fail, okay? Depending on the relative dimensions of each spaces. But I know it's not going to be bijective. It's not going to be an isomorphism. Sometimes because it won't be injective, sometimes because it won't be subjective. Okay? And not an endomorphism because we go from one space to another. So here we go from O4 to O3. That's interesting just to make the before I'm looking at what contains this matrix. What are the possibilities here? So that's not an endomorphism because I don't have the same dimension from, well, it's not the same space. Okay, and that's not an isomorphism because it's not the same space. Can it be surjective? Yeah, the idea is that I've got 4 dimensions and I go to something with 3 dimensions. Okay, so the thing is that I'm losing some information from the domain to the codomain. I've lost something, I've lost 1 dimension. Okay, I've embedded my R4 space into something which has less information. So maybe I'm going to be able to represent everything. Okay, maybe not, but that's something that can happen, right? So surjectivity is possible. Yes?
Mapping is going from R4 to R3, but X, like the polynomial is it an endomorphism or not? Because the space is not the same. But
No, the space is not the same, it's not endomorphism. But if they have the same dimension,
yes.
okay, you can, it won't be an endomorphism, but you can have an isomorphism. Okay. So what would the rank nullity theorem tell me here? What is, so first, so rank nullity tells me it works with the rank and the nullity. Okay. The rank, what's the maximum number I can get for the rank? 3. Okay, I know that the rank is going to be small or equal to 3 because that's the maximum dimension of the codomain. Nullity, what should it be?
It's at least 1.
It's at least 1. Okay, so greater or equal to 1. Why? Okay, because of the rank nullity theorem, I've got that rank plus nullity should be equal in that case to dimension of the domain. Okay? For matrices, get back to everything we saw during the first semester. Okay? Right, so I know that the rank would be at most 3, the nullity would be at least 1 because it has to satisfy this relation. Okay? So if we look at that, so you remember, you know how to, well, we should solve that, but I guess you know how to do this. If not, you should know. Right? So you can put that under echelon form. Well, it's quick. Right? So it's linear because it's represented by a matrix. So for that, there's no problem. So my map is this one. Those numbers. Okay, never mind. So, one very useful thing, whatever your aim, whether you're aiming for the rank or for the image or for the kernel, it all begins by doing the row echelon form of the matrix. Okay, so we'll just begin with the Gaussian elimination. So the first row is going to remain the same. Second row minus first row. So this is my pivot. Okay, so again, now you have practiced that a lot. You know I'm allowed it to combine only with the pivot row. Okay, so row 1 remains the same because it's my pivot row. Row 2 minus row 1. So that's I get a 0. Here I'm getting a 2. Okay, and then I get 6. 6, and then I get 10. Right? Row 3 combined with row 1 and only row 1. So row 3 plus 2 row 1. So I get my 0 here, which was my aim. 20 minus 20, that I get another 0, so that we get something simple. 53. And here's. Okay. So here I've got all the information that I need. Okay. Here I have 3 pivots. My echelon form, it's not a reduced to echelon form, but it's an echelon form. Okay. I wouldn't have a next step if I wanted to put it in echelon form. So I've got 3 pivots. It means that I could consider that these are my 3 columns, and they correspond to those 3 columns that can span my image, my column space. Okay, that comes from the CR decomposition, right? Okay, so I've got that the column space. So dimension of the image is 3, and the image of V is the column space. Sorry, the image of my map is the column space of V, and it's the span of 1, 1, negative 2. Maybe I can simplify this, dividing by at least 2. Okay. Minus 5, minus 4, and 10. Okay. And this one by 3, I guess. You can use as is those columns, but maybe take the simplest one. So 6, 8, 3, and 17. 6.
8 minus 8 and minus 6.
I've just it's the same. Okay, you can keep them as is or look for the simplest one you could write. Okay, right? Yes?
Why did you choose the first 3?
Because they correspond to the first 3, to my pivots. Pivots on first column, pivots on second column, pivots on third column. Okay, that comes from the CR decomposition that we saw during first semester. Okay, that's my OR matrix. Okay, the C is going to contain only those 3 vectors. Okay, and that just makes that you can create B out of those 3 columns. Okay, so the span of these are going to be those 3 columns, right? Okay, so and the kernel, either you work from here or you use the reduced row echelon form. Okay, you remember the one where you put zeros in the reduced echelon form, you put zeros above the pivots. Okay, it's just the second step of it, and you get the kernel of this matrix. Right, and we should find that it's dimension. Okay, of course, because we've got 3 dependent variables and 1 free parameter. Okay, so it's going to have dimension 1. Okay, so everything can be read from this matrix. Right? Okay. So these are things we learned during first semester. Now it should be easy for you to work on matrices. So this semester we go beyond that, right? We go to things that in the end would be expressed as matrices, but we have maybe one step before we go to the matrix, or maybe we have things that can't be expressed with matrices, which are things that, well, in terms of linear maps, which are maps that work on infinite dimensional spaces. Okay, like what we're going to see. Okay, so next one. So map D as differentiation goes from R3x to R3x, takes a polynomial in with degree at most 3, gives you back a polynomial of degree at most 3. Okay? And for if we write this polynomial as function f, it gives you f prime. Question? Okay, why is that linear? Simply because if you take two functions, f1, f2 in R3x, okay, lambda in R, and you apply your map to the linear combination, so you know what that's according to the definition of this map, that should be the derivative of the argument, and then you use always the linearity of things you know that are linear. Okay, in the previous one examples, it was the matrix vector multiplication. Here it's just differentiation that is linear. Okay, you know that the derivative of a sum is the sum of the derivatives. Derivative of lambda times the function is lambda times the derivative of the function. Okay, so you know that this is lambda f1 prime plus f2 prime by linearity of differentiation. And then this is lambda d of f1 plus d of f2. Okay, so image of a linear combination is the linear combination of the images. Okay, so linearity should never be a problem, but it just means that you have to go from this to that. Okay, so always beginning is always like this, end is always like that, if it's linear. What's important is how you prove, how you go from this to this step to this one. Okay, and most of the time it's just using basic knowledge. Okay. Linearity. Then if we look for the kernel and the image and all this, we have many ways to do that. We can work with the corresponding matrix, or we can work with only the definitions. Okay, so let's do the two ways. First way, maybe it's just to relate to what we did earlier. Let's find the representing matrix. Okay, the matrix representation of this map. Okay, so to have a matrix representation, I need a basis. Right, so my usual standard basis is going to be the standard basis of the polynomials of degree f plus 3. Okay, so what is that? Yes?
X squared,
Yeah. Okay, so it's the polynomials. Okay, so each of these. So maybe we raise through linearity. Each of these the notation for the natural polynomial you can express. 1 is the polynomial such that for nx you get the value 1. Again, x is the polynomial such that for any x you get the value x, x2 the one where you get x squared, and x3 the one where you get x3. Okay, so the difference between the capital X and the small x is that these are notations. Okay, but there are implicit notations to define the corresponding polynomials that are given by these expressions. Okay, I won't be too strict if you mistake the small and the big x, but try to think about this difference between the use of these letters. Okay, so if I want my matrix representation, as we said earlier, I just need to know the images of each of these elements. Okay, so I need to know the d of polynomial 1, d of x, d of x2, and d of x3. Okay, so these, I guess it's going to be easy. Derivative of 1, 0. The 0 polynomial, derivative of x, 1.
2x. 3x squared.
Yep, yes?
If we just follow the matrix representation first, doesn't it already prove the numeric?
Yes, sure. Also, yeah. Yeah, linearity should never be a challenge. Okay, and you can make first the matrix representation, but it's a bit yeah. If you make a matrix representation, it means it's because your map is linear. Okay, so yeah, the thing is that you have to prove, if you want to use this, you have to prove that your map, the image of your map of anything, can be expressed using a matrix representation. Okay, we're going to do it. It's not very hard. It's very easy actually. Okay. So now, if I write the matrix representation, I'm going to have in columns the images of my basis items expressed in that standard basis. Okay, so those are not vectors that appear. It's just to tell you, well, that is going to be the constant element from this, the image of d of 1. Okay? So d of 1 was 0, so it's just 0, 1, 0x, 0x2, and 0x2. D of x is 1, so it's 1 times 1 plus 0, x plus 0, and 0. Okay? x2, that's 2x, so 0, 2, 0, and 0. And third one, 0, and 3, and 0. Okay? So this, just to help you remember what rows correspond to what thing. Okay? Alright, so this is the matrix representation, knowing my map is linear. If you want it, like Elijah said, go the other way around. Say, I've got this matrix representation, so it's linear. You still have to prove that this is a good representation for your map. What do we mean? Do we really have that if I apply this to a polynomial? If I do this times the vector representation of a polynomial, I've got the image of my polynomial. Okay? So, let's work on that a bit. That's interesting. If you've got a polynomial in O3x, what does it mean? It means it's going to be something that is written as, well, we've got constant plus the x term plus the x2 term plus the xq term, etc. Okay? So it's going to be a plus bx plus cx2 plus dx3. Okay? That's any polynomial in O3x. It can be expressed this way. Right? I've written here purposely with the capital letters just to show you that it is a linear combination of the basis items. Okay, it's a linear combination of the constant polynomial, of the x polynomial, of the x2 and the x3 polynomials. Okay, that's also one way to express that. Now, if I apply d to p, what do I get? I'm going to get, you're going to get b plus 2 cx plus 3 dx2. Okay, I just did the differentiation of this one, right, according to the definition of my map. But then what we can say is that this is really, if you get the vector expressions of this one and this one, you will have the matrix appearing. Okay? The vector representation of P, well, we can use the same letter, but if you want to make a difference, you can say it's P in basis P, the standard basis. What is the vector representation of that? Yeah, I heard it. Yeah, ABCD. Okay? The coordinates of this polynomial in the standard basis is A for this, B, C, and D. Okay? D of P, this one, in matrix, in the standard basis B, B to C, 3D, and 0. Okay? And what's the relation with this matrix representation? We really have that this one is this matrix times that vector. Okay? We really have that D of P in basis B is actually given also by the matrix. Let's give it some name. Let's call this the matrix D. D times this PB vector. Okay? So, if you didn't want to prove first linearity, you could make this matrix and explain this, right? And then you have that this map is expressed with a matrix, so it's linear. Right? But anyway, that's a useful work because we work often with these kind of things, so you have to be able to go from the polynomial representation to the vector representation. Okay, it's something we often do in the exercises. Okay? And so that if you're looking for the kernel, you can work it with this, right? Or you can work it with the map itself, okay? Kernel and image. All right, so here, well, if I look at the null space of this matrix, I get nothing on the last one. Okay. What else do I get? So I want to solve A, B, C, D. Well, this matrix times A, B, C, D is equal to 0. What do I get? I get that. B is equal to 0, C is equal to 0, D is equal to 0. The only one. Yeah. The only one I don't have any thing on is the first one. Okay? So the null space of this is going to be the span of 1, 0, 0, 0. Okay, so that's the null space of my matrix, which tells us that the kernel of the matrix of the map D is going to be the polynomial that is represented by this vector, which is the constant one. Okay, kernel of D is the span of this. I'm going to write it like this: the polynomial, the constant polynomial one. That's easy. Okay. Okay. Other way to find it, if you didn't want to work with the matrix representation, would be just to solve my map is equal to 0. The image to find the kernel. We could also do this one, curl of D is all the polynomial speed such that D of P is equal to 0. That's just the definition. Now, if I do D of P for any polynomial of R3, we know it's going to be, we've done that earlier, D plus 2CX plus 3DX2. And then what do we use? And that should be equal to 0, the 0 polynomial. That should be the constantly equal to 0 polynomial. Why can I conclude that B and C and D must be equal to 0?
Because the polynomial is equal to 0 when all the coefficients are null.
Yeah. Okay? The polynomial is equal to 0 for all x's, for all values of x, if all its coefficients are 0. Okay, so we get B is equal to 0, C is equal to 0, D is equal to 0. Right, so that P, that's written like this, P of x is equal to constant A. Right, so we can write, if we don't want to use any basis of vectors or whatever notations, it's just the set of P of x that are equal to A for some A in R. Okay, and this for all x in R. Constant polynomials. Okay, and then the image we see either here or here that the image is going to be linear combination of constants, x and x2. So it's dimension 3, we've got 3 parameters. And actually it's going to be polynomials of degree at most 2. Okay, right, so the image. And it corresponds to the column space. Okay, the column space of my matrix. The column space is the second column. Second column, third column, and well, these are the only columns. They have the pivots, and so they correspond to the x, to the constant x and the x2 stuff. Okay, so the image of D is O2. Okay, that's sum up. It's the only space of dimension 3 that is, well, that's how it's defined. As linear combination of constants, x and x2. Yeah?
Can you explain how you find the null space of the kind of
So two ways, okay, to find the null. Find the null space of D, of the matrix. Very, very easy. You're looking for ABCD such that this times ABCD is equal to 0. When it's already on this kind of, it's already nearly diagonal. Just read that. If you make this, that makes B is equal to 0. That's multiplication of that first row with this vector. Okay? Second one, you get 2C is equal to 0, so C is equal to 0. And third one, you get 3 D is equal to 0. Okay, and the last row doesn't give you any information. Right, so that's, you're solving this times that vector is equal to the 0, 0 vector. Right? If you don't like the reasoning on the matrix, just write the corresponding system that you get. Right? Each line corresponds to a line of the system. Okay? Yes?
Why what the C of x is equal to a, is when x is equal to 0.
For all x, okay. If I start by saying I'm looking for polynomials over 3x that are written as a plus bx plus c x2 plus d x3, okay, as an polynomial of 3x, such that this is equal to 0. What do I get on the coefficients? I get that b, c, and d have to be equal to 0, and a, it can be anything. Yes? Okay? So the polynomials that are going to solve this equation are the polynomials that are written as a. Just a constant for all x. For all x in R, this is the polynomial I've got, and I don't have any constraints on my value a, so it could be any value in R. Constant polynomials. Yes. Okay. Other questions? Yeah? The image of D is going to be equal to the span of 1x, x2. It's the linear combination of these three vectors. Okay? If I work on the matrix, so if I'm looking for the image, let me erase that. If I'm looking for the image, I can work on my linear map defined this way, and we see that it's going to be anything that can be written as, so P belongs to, a polynomial Q belongs to the image of my map. It means that Q is written as a constant plus, let me use, I don't know, Greek letters. A constant plus another constant times x plus another constant times x2. This is what I get from that. If I just work on the linear map, I see that if I've got anything that is written like this, I can find one polynomial that was in R3x that will give me this image. What would it be? It would be the one where the b is equal to that one, the one where c is equal to half of this, and where d is equal to 1/3 of that. Okay, so if I am given something like this, I can find one of the pre-images, right? So my image is going to be this one, any polynomial written like this, which I can also write as the span of constants x and x2. And it happens to be R2x. Okay, that's working on the linear map. If I work on this one, right, on the matrix, I'm just looking for the column space of this matrix. Okay, so I'm looking for the column space of this matrix. So it's, you know that it's going to be spanned. This is already the radius touchdown form. Okay, so spanned by 1, 0, 0, 0, 0, 2, 0, 0, 0, and 0, 0, 3, 0. Okay? This vector is collinear to the one where I put 1. It doesn't matter. Okay? It doesn't change anything. So they span the same thing. And this, if you get back to the polynomial expression of these vectors, this is vector constant polynomial, this is vector polynomial x, and this is polynomial x2. Okay? Yeah?
Can we reduce the domain to R2?
Yes? Yeah, sure. Well, that's the whole difference between image and codomain. Okay, I could even say that the codomain is of 5x. The polynomial of degree at most 5. It's true. It's going to be a polynomial of degree at most 5. Just that the image is much smaller than that. Okay, it's not even a polynomial of degree at most 3, it's 2. Okay, so yeah. So this is something we're going to do. Yeah, that's next question actually. Right? So great. So if we are here, what do we know if we answer the injectivity and surjectivity questions? So it's an endomorphism because it goes from one space to itself. It is not injective because the kernel contains non-zero elements. And it is not surjective because the image is smaller, strictly included in the codomain. Okay, so it's nothing. Okay, not injective, not surjective. Okay, and by the way, we can check the rank nullity theorem because dimension of the domain is 4. Dimension of the kernel is 1. Dimension of the image is 3. Okay, so 4 is indeed equal to 1 plus 3. Okay? Now if we do the same thing, can I erase the whole stuff here? Okay? Yes? Yeah, sure. If we do, yeah?
I didn't get the
It's not surjective. Okay. Can I erase that? So what we have found that the kernel of D was spanned by constants. We have found that, which I can also write R0x, if you like notations. We have found that the image of D was spanned by 1x, x2, and that's actually O2x. Okay? So, it's not going to be injective because this is not only 0. And it's not going to be surjective because this is not R3x. Okay, that's all. It's strictly included in that one. Right? There are elements of R3x that are not in R2x3. Okay, so that's the only reason why it's not surjective. But then, the next interesting question is, what's happening now if I reduce my codomain to R2x? I can do it because, well, we see that none of the images go higher than degree 2. So this is something that I put that is still true, still going to be a linear map. I will still have the same kernel, but then I have that the image is exactly my codomain. Okay, so here it's going to be surjective. Okay, the rank nullity is still satisfied because the rank nullity only concerns the dimension of the domain. Okay? Dimension of the domain is 4, still 1 plus 3. Okay, it just happens that now I'm considering that that my map is onto R2x instead of being onto R3x. Okay, so here it's just, it doesn't change the property of the map itself, it's just how we consider it. Okay? The kernel is still spanned by the constant, it's R0 if you want to write it with the polynomial notations. Okay, and then I think we take again the same map, but C infinite. Okay? Can I erase that? Next question is going to be, we still have a map that takes a function and gives you the derivative of your function, but now we're working with functions that are infinitely differentiable. Okay, so this notation, we've used it a bit. Okay, so it's just maps that are infinitely differentiable. Was it true that I can take the derivative of an infinitely differentiable function and I get another one? Yes. Okay. What's the kernel? So this time, we don't have any matrix representation because I don't have any finite dimensional basis for that space. Okay? Sorry? Let's see. Yes, but yes, it won't be. So, if you want to use those words, it is an endomorphism because we go from one space to itself. Okay? It's linear for exactly the same reasons as before. The derivative of a linear combination is going to be the linear combination of the derivatives. Now let's look for the kernel and the image. All right? So let's look for the kernel of D. By definition, it's going to be functions that belong to my domain, such that f prime, if I apply d of f, which is actually f prime, is equal to 0. What are all the functions that give you 0 as a derivative? Constants. Okay. F in C infinite of R, f is constant. Okay. Or you can say f can be written as f of x is equal to a for some a in R. Okay, so we could say that the kernel has dimension 1 in just anything that is going to be a constant. So from this, I know that my map is not going to be injected. You should really know how to show why, if the kernel is not reduced to 0, you don't have injectivity. Okay, you don't have injectivity because it means that if two elements have the same image, okay, that's the definition of the injectivity, then they must be equal to each other, right? So if you have two elements with the same image, it is possible to take one element and add anything from the kernel, and you get the same image by definition of linearity and of the map. Okay, so know how to do that. Okay, so I know that's not injective because the kernel contains non-zero elements. Yes?
How do we know that f is a constant?
Because I know that the derivative of a constant is equal to 0. We're going to work on the image. What would be the image of this map? So I know it's included in C infinite functions. Do you think that it's going to be surjective? Let's try. Okay? What does it mean? Yes. Why? Because the idea is that any linear, any function that is infinite, I can find another infinite function so that it's going to be its derivative or its primitive. Let's work on that. Okay, so maybe can I erase the center? Okay. So if we want to work on subjectivity, what do? We take anything in the codomain and try to see if we can find the corresponding arguments in the domain. Okay, so given G in the codomain, okay, can we find F in the domain? Well, in our case, they happen to be the same. Here I'm considering the codomain, and here I'm considering the domain, such that if I apply D to F, I get G. Okay, if this is true, I've got subjectivity. If that's not true for all functions of the codomain, then it means it's not subjective. Okay, so that's the question we have to ask us. Okay, so let's see that. Can I find G is equal to F prime? Can I find F such that G is equal to F prime?
Yes.
Yes. How can we define it? What? Yes, the integral, the primitive, the antiderivative. We just put, so that's again something like analysis synthesis. If this is true, what does it imply? It implies that F is an antiderivative of G. Okay, if it's derivative, that's the fundamental theorem of calculus. Right? So put F is an antiderivative of G. One of them. One of the minis. Okay? You all want to add plus constant. Arbitrary constant of integration. What does it mean? I can take any antiderivative and add anything from the kernel of my life. Okay? And I will get the same image. Okay? If I've got some F which is one specific antiderivative of G, and I add any constant, anything from the kernel, that's the one you find in the arbitrary constant of integration. Okay? You will get the same image, you will get the same G if you differentiate it. Okay? Alright, so yes, I can find an antiderivative for any infinite function, and that's going to be its preimage. Okay, I can define it. Analysis, this is what we need. Synthesis, well, we put F is equal to this. This exists because G is infinite. I don't have to take any of them, right? If you really want to choose, you can take the one that is cancelling in zero, whatever. That can be an ID. Then we have that D of F is equal to then D of F is equal to G. Hence, the map is subjective. Okay, because this is something we can do for anything in the codomain. Okay. Yes, Déjà?
I was wondering, in this case where G is belongs to C infinity, but assuming another case actually, for example, F is constant, C is just C2.
We will have some other exercises like this. Don't worry. Yes.
I just don't understand how we have proved just by saying that as we see it, we can take the integral. How would that prove that it's subjective? Because we haven't calculated the integral.
No, but I know that I can do it. I know that for any continuous function, so if it's infinite, it's continuous. I know that I can define an antiderivative, and I'm going to call it F. Sorry?
Solution, just that.
Yes, that this is what I wanted to prove. I want to prove subjectivity. I want to prove that if I take anything in the codomain, I can find the preimage. I take anything in the codomain, I'm defining this function. This is a infinite function. Okay, so it's in the domain, and that works. I define my function, and it really gives me this relation. So I have subjectivity. Okay? Right, so we always go back to the definitions for this. I want to find the kernel. What are the functions that make zero? I want to prove injectivity. Do I have a preimage for anything in the codomain? Okay, it's always those two basic questions that we're answering. The ways to answer them depend on the kind of things we have. Right? If you have a matrix, you look for column space and kernel and null space. If you have something that can't be expressed with a matrix, you just go back to the definition. Next one is we're going to do something very similar, but with instead of differentiation, we do the integration. So next one is so we're going to look at map I that goes now from R3x. I have to take one order more this time because you know that if I integrate another 3 polynomials, I get another 4. And if I want to map well defined, I have to take one of the specific antiderivatives, the one that is going to cancel in 0. Okay? So this is how I'm defining my map. Okay? It's well defined because for anything, I can really define uniquely the image. I wouldn't be able to define the correct map if I just say it's just an antiderivative of it. Because I've got an infinity of possibilities. Okay, if I want to define correctly a map, I just have one single image, right? So one function, I've got one single image because I'm checking the antiderivative that is 0 and 0. Okay, so that's worth noting. Okay, that's one of the specific primitive of this function. Yep.
I didn't follow it. So if we find that, then we can conclude.
Nothing. It was just to tell you that this is a well-defined map, which you don't have to prove. You assume that the question is well asked. But the relation is that often students write things like, well, I've got, for one map, I've got one single image. Then it's whatever. No, it just proves that we have one well-defined function. Okay? We have one function that takes an item and you get a single image. That's the minimum we ask. Okay? And that was to explain you why I had the 0 and not just primitive. I wanted to do something similar as the previous questions which were for derivative. I just had derivative in general. Here, I just don't have integration in general. Because integration, I've got many in primitive for one single function. I've got an infinity of those. So I have to put one specific one.
It could be given.
Yeah, sure. This usually, or I will ask you, prove me that it's a well-defined map, one image, one well-defined for each in the element. Okay, but it's not usually the question. Okay, so, but now the question is, what is the kernel, image, and so on? Okay, again, many ways to do it. As we are working with polynomials, we can work either on the matrix representation or on the on the map itself without matrix representation. Okay, so let's do the matrix quickly. If I want to do the matrix, I have to take the image of each element of the standard basis. Okay, standard basis of R3, 1, X, X2, X3. That's always an interesting work in doing. What would be the primitive of constant 1? The primitive that is X. Primitive of X that's cancelling in 0. Okay, so indeed, I would have, so how many columns and rows for my matrix?
4 rows and
4 columns
oh,
And 3 rows.
yeah.
and 5 rows.
Oh, yes.
Yeah, okay. So when we will check the rank nullity theorem, it's going to be related to the dimension 4. Okay, so my matrix would really be so 0, 1, 0. So I've got 5 of those. 0, 0, 1 half, 0, 0, 0, 0, 0, 0, 1/3, 0, and 0, 0, 0, 0. 1/4. How many? I've lost my count of zeros.
I think it's 6.
Did I do one too many? So that's corresponding to constant, to X, to X2, to X3. I've got one too many.
In the last 2, there's too many.
So what did I do?
Last 2 columns.
Let me check. So I want the image of 1, of X, of X2, and of X3. Okay, and that's going to be expressed in the basis 1, X, X2, X3, and X4, because now I've got I need dimension. I need degree 4. Okay, so image of 1 is, we said, was 0, 1, X2, X3, X4. Image of X was going to be, we said 1 over 2 X2. Okay, X3, X4. Image of X2, 0, 0, 0, 0, 1 over 3. And image of X3, 0, 0, 0, 0. And I still have something wrong with this. So 0, 0, 0, 0, and 1, 4.
Yes, the one before. The third row is the third column has too many.
So let me erase that. Okay, so this would be my matrix representation.
The third column still has 1 too much.
There's one column that, yeah.
Yep.
And that's, so this, you will just have 1, 0 here. Okay, I would be able to do this simple one. No, this, I've got the right amount. It's just that now they don't look on the same row. Okay, that's what we should have. Okay? So from this, what can we read from this matrix? So what is going to be the map that gives me 0? What would be the kernel of this matrix? I already have something that is diagonal here. Okay? So if you want to solve this times, okay, so that's the matrix representation. I would apply it to a polynomial of R3x. which is expressed as A plus Bx plus C x2 plus D x3. Okay, so I'm basically looking for A, B, C, and D. Such that this is going to be equal to 0, 0, 0, 0, and one more. Okay? So my matrix is a matrix with 4 columns and 5 rows. So that is going to be working on elements of R4 and give you an element of R5.
Matrix has 5 rows, but
Yep.
there's D is the 4th letter. So
Yes?
how does that work?
Because that's what I wrote. When you're doing the matrix vector multiplication, and on the right, you've got 5 items. Matrix vector multiplication, this times that gives you the first item.
Oh, yeah.
Okay? You have to have the same number of rows here as you have as columns in that first one. Yeah.
Is it the span of the zero vector?
Sorry?
The span of the zero vector?
Span of the zero vector.
0, 0, 0, 0. Because,
So if I'm looking for the null space.
yeah,
Okay? Yeah, we're going here.
because it's
Right. Okay, so if I want to solve for the null space, this is what I want to solve. Okay? The first thing doesn't give me anything because it's just 0 plus 0 plus 0 plus 0 is equal to 0, right? Okay, I haven't learned anything. But if I do the second one, that just gives me A is equal to 0. 1/2 of B is equal to 0. 1/3 of C is equal to 0. And 1/4 of D is equal to 0. Okay, so they must all be equal to 0. Right? So the kernel of, well, the null space of this map is really going to be the 0 vector. The null space, have I given a name to this map? Map I. No, not I. I is just the identity. Map M. Okay. That's my matrix M. The null space of M is just 0, 0, 0, 0. Okay, and the kernel of I is just the 0 polynomial. Don't write span. Okay, it's just one item, and we can't write the span of some 0 because then it's anything is in the span of 0. Okay, because or nothing is in the span of 0 apart from itself. Okay, so don't just write that it's one element. Okay, so that's working on the matrix, and so if we work, and if we go let's finish on the matrix. If we take the what's the image? The column space of this matrix. What are my pivots? Okay, so it's going to be dimension 4. Okay, in a space of dimension 5. And they correspond to x, x2, x3, x4. Okay, so the column space of the matrix is just 0, 1, 0, 0, 0, 0. 0, 0, 1, 0, 0, or 1/2 if you like, that's just the same vector. Okay, so the common space is the span of those 4 vectors. Okay, all the columns that contain a pivot, and these are, I've got 4 pivots. Okay, so it has dimension 4, right? And if I write this with the polynomial representation, I can write that it's going to be the span of the corresponding polynomials. So that's x, that's x2, x3, and x4. Okay, and so we really have the rank nullity theorem satisfied. That has dimension 4. Kernel has dimension 0. So this is equal to the dimension of all 3x. My polynomials are of a degree of -4. So this is injective. This is not surjective because this image is strictly smaller than all 4x. Well, maybe I should have asked you. Why is it? So why did I say that the image is smaller than all 4x?
One, if this one was 1x, x2, x3, x4, then it could have been R4.
Yes. Okay, for many reasons. One of the reasons is that I don't have enough dimensions. Okay, I've just got 4 and I need 5. And what is going to be excluded in the image?
The constant.
Constants. Okay, yeah. I can't find something that's I can't find a constant function such that would be the primitive of something else. Okay, apart from 0. Yes?
Did you say it was injective?
Yes, I said it was injective. Why did I say that? Because the kernel contains only the 0 element. Okay, so that was working on the matrix, but you could really do all this on the function. Quickly on the function. If we have a polynomial of all 3x, it means that p of x is written as a plus bx plus cx2 plus dx3. Okay? If I apply my map I to this polynomial, what does it give me? No, I'm integrating. So ax plus b over 2x2, this c over 3x3 plus d over 4x4. Okay? That is, you didn't need to do the matrix. You could also work directly on that. If I've got a polynomial in my domain, so it's written like this, I apply the map, this is the polynomial that I obtain. Okay, and here what you see, you directly see that the image is spanned by x, x2, x3, x4. Okay, so we already get here that the image of I is the span. So I could have written this with a capital letter that was exactly the same thing. If I say, that would have been better, actually. Okay, just to say that I'm taking my polynomial in R3x, which is a linear combination of these items. I can make the image that's going to be a linear combination of these items, and I know that it's going to be then in the span of x, x2, x3, and x4. Okay, so I've got already the image that has dimension 4 and not 5. And how do I get the kernel? Simply make this equal to 0, just like we did before. Make this equal to 0, we get a is equal to 0, b is equal to 0, c is equal to 0, and d is equal to 0. So only the 0 element, the 0 polynomial. Okay? All right, so that was working on polynomials. Same thing, but C0, C1 function. So what's going to change? I can't make the matrix representation, and I don't have this explicitly because it could be any continuous function. So now we change to C0 for the domain C1. Again, we still have the same definition, right? So, and I know that if f is continuous, I know that there exists a primitive of it. Okay, that's basic definition of primitive. Right, so do we have, what about the kernel? So again, we're doing, I want to find the f such that this is equal to 0. Okay, that's a function. That's the 0 it should be equal to is the 0 of C1. Okay, meaning the 0 function. So what function has a primitive for no, the contrary? For what function do I have that its derivative is going to be equal to 0? Yes, but I know that this is also a function that is cancelling in 0. So the only possibility is 0. Okay? So we get, all right, let's sum up. We get from that f of, what? We get that f prime of x is equal to 0, so f is a constant, and we get that it's a constant, and so we get that f is equal to 0. Otherwise, that would be equal to x. Okay. All right, so we've got that the kernel is equal to only the 0 function. So from that, again, we can conclude that we have injectivity. No, that's something wrong. Okay, well, more precisely, sorry, there was something wrong. What is that? F is in C1, is in C0, so it has a primitive, let's call it capital F. Okay, and this integral is always equal to capital F of x minus capital F at 0. Okay, that's the fundamental theorem of calculus. That's independent of looking for this equal to 0. Okay? All right, so now if I say that this is equal to the 0 function, okay, it means that f of x is, capital F of x is a constant. It's equal to always the same value, right? I didn't say it's 0, just that it's going to be equal to the same value. All right, and now if we have that small f is the derivative of capital F, we get that small f is equal to, that's good. Okay, so that's how we get that the kernel of this map is reduced to the 0 function. Now, let's do the other way around. is that map surjective? So we should answer, do we have for any function g in C1 that I can find a corresponding f such that I of f is equal to g? Okay, so surjectivity or image, it's going to be both go together. Okay, because if you look for surjectivity, you may obtain some restrictions on the possibilities. Okay, so that's why we're doing it that way. Right, so subjectivity, let's take G that is C1. Can we find F in C0 such that I of F is equal to G? Okay, so analysis part, G of X would then be defined as the integral of F. Can we find F such that this is true? How would you find F if you're given this kind of relation? Yes? Yeah, exactly. Differentiate, how would you, if I give you this kind of relation, how do you extract F from this? You do the derivative. Okay? So that's going to be G prime. So you do the derivative on both sides. And you get, on this side, you get G prime of X is equal to F prime of X. Fundamental theorem of calculus. F of X, sorry, yes. Okay, so I can do it. I know why? Because G belongs to C1, so I can make its derivative. Right? I can make its derivative and it's going to uniquely define a C0 function that is F. Okay? So yes, it's surjective. It's injective, it's surjective, it's bijective. It's an isomorphism. Okay, so yeah. Yes?
I don't get the end of this and the first subjectivity proofs. Like we get J prime of X is equal to F of X. How do we know that this means that it's subjective?
Okay. Surjectivity means we want to answer the question, if I take anything in the codomain, can I find the corresponding privilege? Okay? So, we take something in the codomain. Let's call it G. Can we find F in the domain, C0, such that the image of F is equal to G? Okay, that's basic question, right? Now, what does it mean for our map? It means that I rewrite this equality. G of X should be equal to that primitive, the primitive of F that cancels in Z. So, can we find F? Yes, because we know that when we've got this relation, it tells us that F is the derivative of G. Okay?
And since G is derivable,
And since I can do this because G is in C1, it means that I can define F. So if I can define F, my map is then surjective. Okay? All right. erase that. Now, what does it change if instead of taking the codomain of C1, if I tell you that the codomain is actually C0? Exactly, yeah. So it doesn't change the kernel, because the kernel is acting on the domain, but it may change the image. Well, it may change the subjectivity property more exactly. Okay? Can I find, for any C0 map, something that will give me that the image of F is equal to this? What would fail here? Yes. Some items in C0, we can't write this. Okay, so a reminder, functions that belong to C1, they are continuous and their derivative is continuous. And it is a strict subset of C0, functions that are only continuous. Okay, some continuous functions may not be differentiable. Typical example, the square root, the absolute value of it. It's a continuous function, but it's not differentiable. Okay, it's not differentiable because you've got derivative constantly equal to 1 plus 1 on the right-hand side of 0 and negative 1 on the left-hand side. Okay, so what changes when we change the domain? It's still a well-defined map. There's no problem about that. It's just that there will be functions, those that are only continuous, for which I will not be able to find a preimage. Okay, so functions that are in C0 but not in C1, we can't define a primitive. No, yes, we can define. Yes, no, that's it. No, we can't. It's not that we can't define a primitive. We can't define its derivative. We can't put g prime of x, g of x is equal to the primitive of some function that is continuous. And yeah. Okay, so let's, we will have done completely that one. And the last one, from that worksheet. So we've got the map E that goes from C1 to C1, where I take F and take F prime plus F. Okay, so if I'm looking for the kernel of that, what should I solve? What should I solve if I'm looking for the kernel of E? So I'm taking a function and the image of my function. So I'm looking for f. Okay, such that if I add f and its derivative, which is something I can do because I know that my function is C1, then that is equal to the 0 function. So the 0 of C1. So it means that for all x, well, it's the 0 of C1, the function that is equal to 0 for all x. For all x, we want to solve f prime of x plus f of x equals to 0. What's the solution of this?
It's going to be k exponential minus something.
Yes.
Minus 1.
Okay, yeah, sure, that's it. Right, so that's, well, you remember how you do that, minus f of x, we assume it's either it's 0, we know that the 0 function satisfies that we're going to assume f is not 0, so you write it that way, you've got f of x on this side, you got 1 on that side, you integrate, you put the log, well, it's just the solving of a first order differential equation. Okay, you put the log, so log of f is equal to minus x minus t, and then you take the exponential, right? So we get that f of x is equal to any constant times exponential of minus x. Okay? So we're going to work later on again on differential equations. But this is something you've worked a lot on last year. We've reminded that during first semester. This is how you solve this equation. The homogeneous first order constant coefficient equation. Right? So, do we have injectivity? No. Right? We've got an infinity of functions that solve this equation. If you want to write it as a vector space, you can write that it's going to be the span of E of minus x. Okay? So it's not injective. The kernel has dimension 1, even because it's spanned by one function. Is it surjective? So what do we want to answer when we ask about subjectivity? Well, I should have left that written, at least the first part. Can we find for any g that belongs to C1 f such that f prime plus f is equal to g? Yes? Which is?
We use the antiderivative and then
the question is, can you solve this equation? How would you do?
Just integrate on both sides. No,
Integrate on
sorry.
both sides?
No. Oh, no, you can't. Because it's C1. It's not C2.
If I say, can you solve, so you know how to solve f prime plus f is equal to 0, you've just done that, you get this exponential. F prime plus f is equal to a constant. Come on, guys. F prime plus f is equal to x. X to whatever. Yes? Well, you know how to solve that. When it's a constant, you know you're looking for a constant. Yeah? Okay, you've got one actually. You're looking for a particular solution. When you've got a polynomial, you're looking for a particular solution that is a polynomial. Okay, when we have trigonometric functions, you're looking for also trigonometric functions. But that's one way to solve it, with particular solutions. What is, in general, if you don't have anything specific, it has a name. So I didn't hear. We're looking for a complementary solution, but when we don't have any specific kind of source term, what is the name of the method? Yeah.
I don't remember the
Variation of parameters.
Oh, yeah.
Okay? You make that your function is actually going to be written as, instead of a constant parameter, okay, you take a function. Okay? Right? And then you plug that in the equation and we get something for K, and it's always solvable if G is in C1 in particular. So we have surjectivity. Okay? So yes, by variation of parameters. Okay, so it's not injective, but it's surjective. And what do we find again? You talked about complementary solution. We find the complementary solution by this method, and you can add the homogeneous solution, which tells you that when you want to solve AX is equal to B for a linear map, you can take anything plus anything that belongs to the null space or to the kernel. That's exactly the same idea again, right? If your map is linear, if your equation is linear, you can add to your specific particular solution anything that makes 0, right? Okay, so I guess we didn't have time to do the next worksheet at all. So I hope this has clarified your ideas on this topic. Okay. So try, however, to work on the worksheet 3.4. I'm going to answer some questions anyway. Again, also about the previous ones that we did.